Hello physics students. So in this video, what I'm going to do is I'm just going to show you two demonstrations that are explained away by refraction. So in this demonstration, what I have is a very strong light source right here, shooting light in a beam like this, and then this piece of paper it has a slit in it, so it creates like a narrow beam of white light, right? White light you could see. And then that narrow beam falls on a piece of glass that's triangular in shape. You probably don't see it too well, but here's another exact triangular piece of glass like that. And if I bring it closer, you could see the cross section is an equilateral triangle. And then, of course, it's, like this is a little chipped up. That one's a little better shape. So what happens to that light when it encounters these surfaces? So the first beam of light, what I've arranged it to do is strike the glass at a glancing blow like this. So that will then, of course, refract. Now, which way does it refract? So what I'm going to do is just put another wire here to indicate a normal. Remember, a normal has to be perpendicular to the surface of the glass. The surface of the glass runs like this. So this white wire is approximately at a 90 degree to that. Now this light is going, well, it's a wire, but pretend it's light going from air to glass. Does the wire or the light bend toward or away from the normal? I'll create a pause for you to decide. Go ahead and make that decision in your mind. Okay, hopefully you said towards the normal, so this light turns like this and bends closer to the normal. And then what happens is it continues and strikes this other surface. So notice how it kind of made like a left turn, right? It turned that way towards the normal. It strikes the next surface up here. Now I'm going to put this wire to represent the normal, perpendicular to the glass surface. We've got a normal. Does that light going from glass to air, does it now bend toward or away from the normal? I'll create a pause for you to decide. All right, hopefully you said away from the normal, so that will turn like this. Notice it's another left turn. So then the light emerges into the air, but in the process, the glass made it it was going like this, maybe towards the ceiling in this view, and then it turns left, and now it's going suddenly almost horizontally. So two left turns, a dramatic turn of the light. Let's see what happens as a result of those two refractions. So I've reconfigured, we see another view, the opposite side, here's the light source, there's the slit, the prisms or the glasses on the other side over here. And then you see some light dots on the screen over here, and we can't really see that well what's happening with the lights. So what I'm going to do is turn off the lights of the room so that it makes a more dramatic contrast, and then I'm going to zoom in on the spot on the screen. So. All right, that looks about right there. Okay, so what you should see is that we get the white light turning into colors. And basically you've seen this is a rainbow. You see over here on this side, you see the colors are red. Then you might see a little orange, yellow, green, a little bit of green right here, and then blue and violet. So we get a little bit of a rainbow. So the question is, how did that happen? We started with white light, as you can see right on this screen over here. Right there, that's the original light, and it's white, and somehow that double bending of the light, bending twice by a piece of glass, separated that white light into colors. So what I'm going to do is now explain why that happened using refraction and Snell's law. So why did that happen? To answer that question, you need two facts to explain that phenomenon. The first I already mentioned briefly, and that's that white light is actually a mixture of all the colors of the rainbow. If you were to shine all these lights simultaneously into your eye and your brain would perceive that as no color, white light. Pretty interesting. So this is already a blending of all the lights. Well, then now the question is, well, then how did this glass separate it? That's what you need the second fact for. So at the time when we were studying index of refraction, I did not mention the fact that there's a frequency at the top of this table for a reason, because there was already enough information for you to digest at that point. But why is there a frequency up here? Well, the reason why is because when the scientists did experiments to determine all these values, they did it only for this frequency, which actually corresponds to yellow light. But the truth is, like for example, flint glass having an index of 1.66 for yellow light, you would have to do a separate experiment for every single color to get different indices of refraction for each color. Well, I looked up, some values online, and for the glass that's typically used on prisms, the index for yellow light is 1.62. But for red light, notice it's slightly less, and for violet light, it's 1.665 more. And so what that means that when the light came in, and as I said, it bent twice, so it bends once here, like this makes like a clockwise turn, and then bends again. The red light, because the index was the least, it bent the least and ended up here. Whereas the violet, with the index being greater, it causes more refraction, a more dramatic bending, which then makes the violet light down here. And then so that white light splits up because the indices are actually a function. So go ahead and copy this down. This is now the explanation. Copy this down in your notebooks. And if you don't have a marker, that's okay. Just write out the rainbow colors in your notebook. All right, so that was with glass, but obviously there are rainbows in the sky. A similar effect happens with water droplets bending, the light bending at both surfaces, and it separates the light. And that's why only after a rainstorm or when there's moisture in the air can you see a rainbow. Without, when it's just clear air, you don't get any rainbow effect. All right, so that's dispersion, the creating of a rainbow effect. Let's move on to the second demonstration. So what I have here is a bottom of a plant pot that's going to serve as a dish, a bucket of water, and this washer here, which I'm going to tape to the bottom of this pan here so that it can't move. And then what I'm going to do is just set this over here, and then I'm going to slide the camera back. So this may be a little choppy, but I don't want to stop the camera because I don't want it to look like I'm cheating. I'm just going to move this back until the washer is no longer visible, because we won't be able to see over the rim of the dish. Let me zoom in a little bit. So you see, if I go closer, we could see the washer. If I pull back a little bit, now the washer's too low for us to see it. Up a little bit more. And let me get zoomed right in. Okay, that looks good. Now all I'm going to do is I'm going to walk here. I won't go in front again. I don't want you to think I'm cheating and having someone swap the dish out. I'm just going to come over here and let me turn this. And what I'm just going to do is pour water and fill up this dish hopefully without moving it or making too much of a mess. And you should see that suddenly the washer appeared, and all I did was add water. How did that happen? It's like a little magic trick that suddenly the water makes us be able to see past this rim over here that we couldn't see past before. Well, if you're thinking it has something to do with refraction, you're right. Let me switch back to the desk view so I could explain with the concept of refraction. So by the way, that isn't just a cute little demonstration that I did to amuse you, although hopefully you found it enjoyable, but it is part of the curriculum. And the reason why is because refraction causes people to underestimate the depth of objects. So refraction and depth illusions, that coin in that dish, when the water was present, suddenly felt or appeared to you as if it weren't as deep as it really was. could see over the rim. It's as if that coin were lifted out of the dish slightly, like an inch or two, back into your vision. And the reason why is because just imagine here, very often this is used to, you know, like people talk about spear fishing to explain this. Imagine you're trying to spear a fish. Throw a spear, you're a primitive hunter, and you see the fish and you aim the spear right at what you see. You're going to miss, because what happens is the light comes off the fish, and when it comes to the surface on the way to the hunter's eyes, it does not travel straight. Light bends when it goes from index of water to index of air, 1.33 to 1.0. Smaller index, it's going to bend away from the normal and then go to the hunter's eyes. And so that bending, your brain doesn't perceive that. You need to think about it, because what happens is your brain always assumes light travels along a straight line. So it doesn't detect this bend, so it thinks the fish is traveling straight. It thinks it's here, higher up than where it really was. So the fish appears here, it's an illusion. The fish's actual location is down here. So water makes submerged objects appear at a shallower depth than they really are. So go ahead and take a moment to copy this diagram down. Okay, now, so if you were spearfishing, by the way, I believe it's illegal because it's inefficient and it tends to maim the fish and kill a lot of fish. So I think it is illegal, so don't spearfish unless you check up on it if you're interested in fishing. But nonetheless, if you were spearfishing, maybe you were stranded on an island, you had to catch fish this way, what you would do is you would see the fish and then you would actually aim to miss it. It's like the fish would be here and you would be aiming underneath, and you think that you're going to miss, but when the arrow goes in, and it's like the image is here, but the arrow goes in, it hits the fish, and you'll hit it directly by aiming deeper than what you think the fish really is. If you were using, maybe you're stranded on a desert island with a high-powered laser rifle that kills fish with lasers, well, obviously, why would you have that if you were stranded on an island? But let's suppose you did. Then you wouldn't have to compensate that way, because the light from the fish would bend, and then when you shoot the laser, the laser light would bend the same and reverse the path and hit the fish. So you would actually aim at the fish with a laser. With a spear, you aim below it. All right, so those are the two demonstrations. Again, both of these are part of the curriculum, just little concept questions. I hope you enjoyed them. I hope you enjoyed the video. I'll see you in the next physics video.